Hello everyone. Thank you for being here. Today I'll be presenting our recent work on LLM-assisted crossover in genetic improvement of software. This is a joint project between Peking University and UCL, and I worked on it with Sergey, Mechtaev, and Justyna Petke, our supervisors. The idea behind the study is very simple, but I think it's quite powerful. So the idea is, can we use a large language model, like for example ChatGPT 4, GPT-4, to perform the crossover step in genetic programming for us? This is an initial exploration to test whether this idea is viable and worth pursuing further. And what we'll see today, what I'll show you, is that not only does it work, but it actually might perform better than traditional crossover methods. So let's continue. What motivated this work? First, we're seeing the effects of the so-called end of Moore's law. Hardware improvements are no longer delivering the kind of performance gains we relied on in the past. So now optimizing software has become much more important. Secondly, modern code bases are huge. So manually optimizing them is just not scalable. It is slow, expensive, and very error prone. So that's where automation, especially search-based software engineering, comes in. And also, one key step in genetic improvement is the crossover. But traditional crossover methods, like for example uniform or point-based, do not really understand the context of the optimizations being made. They are combining edits a bit randomly, which often results in non-viable or ineffective variants, and a lot of wasted search effort. So this brings us to our idea. Why not just use LLMs? We have seen how popular they have become the last few years. So since we know that large language models are trained on both code and natural language, they can understand syntax, structure, and dependencies. So they might be the perfect fit for acting as a smart, context-aware crossover operator. If we can use an LLM intelligently to select which edits to combine, we hope to produce more surviving offsprings, generate fitter variants, and also in general guide the search more effectively overall. Before diving into our method, let me briefly just explain the basics of genetic improvement or GI. I'm sure you are more than familiar with them, but let's just go through it very quickly. GI is an automated technique that uses evolutionary algorithms to improve software performance. It is inspired by natural selection. We start with variants of a program, apply transformations, and try to evolve better versions. There are two main types of changes we can apply: mutation or crossover, as you can see here at the bottom of the screen. Mutation introduces brand new edits. It explores the search phrase by adding random changes, while crossover, on the other hand, combines two parent variants to create a new child variant. This idea is to mix and combine good traits from each parent. So in our work, we will focus on the crossover operator and not mutation, and that's very intentional. The reason is that we want to leverage the creativity and contextual understanding of the LLMs, but in a more controlled way. So crossover gives us a predefined set of possible edits, the edits already applied to the parents, and the LLM's job is to select and combine them in an intelligent way. So we get the best of both worlds in a way. We can get the LLM's reasoning ability and code understanding on the one hand, but we are able to still keep it grounded and avoid hallucinations or introduce totally unrelated changes, since the LLM will not have to make up completely new changes. It will just have to choose from the already changes of existing changes that the parents have. So let's also take a quick look at the traditional crossover operations we use in commonly in genetic improvement, which we will be comparing our new LLM crossover operator with. These are five very commonly used methods that are used for crossover. They all work by combining the edits from two parents, but they do it in slightly different ways between each other. We have one-point crossover, which picks a single point in both parents and swaps edits after that point. Two-point crossover is a bit more flexible since it selects 2 points and swaps the segments in between. Then we have concat, which just appends all the edits from one parent and the other. It's quite straightforward. Then we have uniform word-cut, and finally uniform inter, which try to interleave the edits from both parents more evenly, and they either do it before or while combining them. These operators are simple and lightweight, but they're also completely unaware of what the edits actually do. They don't consider the structure of the code, they don't consider the parameters being combined, they don't see if the edits are compatible with each other, or whether they make sense together. So while they can sometimes stumble on good combinations, they are also waste a lot of time producing broken or ineffective variants. This is the gap we're trying to address here with our LLM-assisted operator, a crossover operator. Let's move on to describing the operator itself. The idea is simple. Instead of randomly combining edits with any of the methods shown before, we ask the LLM to choose which edits to apply and propagate to the child, and we give it the right context to make that decision more intelligently. The prompt you see we send to the LLM includes the original variant, which means the base version of the software without any improvements, the two parent variants, each with their own set of edits and fitness scores, how well they perform. Then we can also give it some documentation, which helps the model understand what each parameter or function of the code do. And optionally, we can also give some instructions about the goal. In our case, we're targeting runtime improvement. We're telling the LLM what we're trying to achieve through our optimization process. With this input, the LLM is asked, based on what you see here, which edits from the parents should we combine to create a good child, in the sense that it's gonna get as much fitness as possible. This gives the model enough grounding to avoid hallucinations. With the LLM, the LLM is asked to select the new child, and it allows it to reason about the context dependencies and likely performance impact that the edits it will propagate will have on the final variant. This is where we start to go beyond traditional crossover. We're not just blindly combining edits, we're guiding the process with an intelligent agent that understands the code itself. To evaluate the LLM-assisted crossover, we again use the MACBI framework. I think this has been discussed a lot today. Let me go through it a bit as well. This MACBI is a tool specifically designed for search-based software improvement. It's a great fit for that kind of experiment here for several reasons. First, it's language agnostic, so everything is translated into XML, so it can work on different programming languages like C, Java, Python, etc. Second, it supports multiple types of modifications, so we can see what the effect of LLM-assisted operator is going to be for both structural changes like, let's say, source code edits, or even parametric changes like tuning configuration values. It also supports multiple search strategies, include genetic programming, which is the one we used here. And finally, it's written in Python and well documented, easy to modify, which helped us a lot and made it very convenient for us to swap in our own crossover implementation. On the right hand, you can see how MACBI works. It takes an original program, converts it into an XML-based representation. It uses a search algorithm, in our case, genetic programming, to apply edits and generate variants. Each variant is evaluated using a fitness function. In our case, the fitness function is going to be runtime improvement using Linux time. So this is how we're going to evaluate how good each variant is, by trying to lower the execution time, the Linux execution time. And then over time, the system evolves towards the fittest variant, the version with the best performance. By plugging in our LLM-assisted operator, we can compare it directly against the traditional methods that MACBI already supports under the same conditions. So let's see a motivating example from one of our benchmarks, which is a compression library. We have two parents. You can see on the left parent 1, which W bits equals to 30 and level equals to 2. And on the right parent 2, which has strategy equal to 2 and memory level equals to 8. What is important here to understand is that the two parameters that really affect runtime is memory level and level in general. With traditional crossover, though, we might get some we might get a child that just randomly combines edits. For example, here on the red box, we can see a potential child that might be generated, which doesn't propagate either of the useful parameters. But that combination here is not great because it doesn't improve runtime because of that. It might even make things worse than the original parents, making us waste some time during our search. On the other hand, with LLM-Assist crossover, the model with the documentation provided gets to understand which edits are useful, and with the improvement goal in mind, which in this case is reducing runtime, as you can see, decides to keep level equals 2 from parent 1 and memory level equals 8 from parent 2, which is much better combination. It lowers the compression level for speed and increases the memory level for performance. So instead of just mixing edits blindly, the LLM uses context to intelligently propagate the useful changes. This is the kind of reasoning traditional methods just do not have access to. So let's now talk a bit about our experimental setup. We evaluated the LLM-Assist crossover on 7 benchmarks, covering a mix of domains and programming languages, included SAT solvers, a compression library, scientific computation functions, and even an AI planner. Some of these, like SciPy and Zlib, were used only for parameter tuning, since the source code wasn't suitable for modifications. Other, like Minsat and Weka, I think I'm mispronouncing, but I'm not sure, were used both for parameter tuning and source level edits, giving us a total of 11 experimental scenarios. All of our experiments were run inside the MagPy framework using GPT-4o Mini as the LLM of choice. This is a lighter weight version of GPT-4. It has a good balance between performance and cost, which makes it a practical choice for repeated API calls during crossover, for even more to make this idea even more scalable, in case we're talking about hundreds of thousands of calls. We used a population size of 20, and each run lasted for 11 epochs. And crossover was emphasized with a relatively high crossover rate of 0.6 compared to 0.2 for mutation and 0.2 for elitism. This setup was intentionally designed to stress the importance of crossover so we could really see how well the LLM-guided version performs compared to traditional operators. So let's now look at the results, starting with the average runtime performance of the generated variants. We compare all 6 crossover methods based on 2 metrics: AOF, which is the average optimal fitness, which is the runtime of the best variant found by each method, and average fitness across all variants, giving us a sense, and AF, this is the average fitness across all variants, which gives us a sense of overall quality and consistency of the variants produced. As you can see in the table, LLM-Assist crossover outperformed every traditional method. It achieved the lowest AOF at 4.477 seconds, meaning it consistently found the best performing variant in the end of the search. And also it had the lowest AF at 5.834, showing that it didn't just get lucky once and find a good variant in the end. It actually consistently generates better variants overall. And it also had the best average ranking across all benchmarks at 2.27. To put it into perspective, this means that there is around an 8.5% improvement in optimal performance and 6.1% improvement in average performance compared to the average of the 5 traditional methods. These results suggest that the LLM is successfully guiding the search toward better performing edits, not just occasionally, but consistently across benchmarks. Let's see now beyond just producing better variants. We also wanted to see which crossover method gets us to improve performance the fastest. So how to answer that? We looked at how many variants each method needs to reach different improvement milestones: 25%, 50%, 75%, and 100% of the best observed fitness for each benchmark. If a method failed to hit a milestone, we applied a penalty of 250 variants, since it was the maximum number of variants allowed per run. So, and again, as we can see here, the LLM-assisted crossover comes out on top. For example, it reaches 25% improvement in just 39 under 40 variants and hit the full 100% improvement in 209 variants, both of which are faster than any of the traditional approaches. To compare, the next best method, uniform concat, needed 56.45 and 227 variants to hit those same milestones. On average, the LLM-assist crossover reached performance goals in using 25.6% fewer generated variants than the other methods. This shows that it's not just better in terms of final results, but it's also more efficient, helping us reach strong solutions faster than the other traditional approaches. So with less computational cost. Now, the final research question was, how well does each crossover method preserve functionality? How can we measure this preservance of functionality? We measure it in the sense of viable variants, variants that successfully compile and pass tests. So we're trying to measure how many of these viable variants does each crossover method produce. This is especially important in genetic improvement since non-viable variants waste search effort. And it's particularly challenging in source code edits where structural incompatibilities are common. So if you make some sort of source code edit, it's probably going to mean that the functionality is going to be affected somehow. We tested this across all our benchmarks, both source code edits and parameter tuning. And here's what we found in the end. The LLM-assist crossover produced the most viable variants with an average of 194.45 out of 220 possible. That's close to the theoretical maximum and 4.8% more than the average of the traditional methods. And the next best approach, the next best operator was again uniform concat, which came in at 187.73. We believe this is important. This improvement is due to the LLM's ability to reason about edit compatibility, and it avoids introducing changes that break the code. So overall, the LLM-assisted methodology not only finds better and faster variants, it only produces more functional ones, which is crucial in real-world applications. So let's briefly look at how our method compares to existing crossover approaches. Traditional crossover, as we just talked, like one-point or uniform crossover, are simple and cheap, but they operate blindly. They have no context awareness and randomly select modification, often producing ineffective or broken variants. Then we have some semantic and context-aware crossover methods that try to address this by analyzing program behavior or structure. And examples include semantically driven crossover and locally geometric semantic crossover, which, while powerful, these methods are quite computationally expensive and hard to scale as they rely heavily on program-specific analysis. And lastly, we have machine learning assist crossover, such as deep neural crossover. These models use adaptive learning to guide the gene selection, but they require significant pre-training, domain-specific fine-tuning, and extra data. What makes our approach of the LLM-assist crossover different is that it's context-aware, thanks to the LLM training. It works out of the box, so you no need for any retraining or extra data. And finally, it's general purpose. So it's applicable across different languages, different benchmarks, different optimization goals. You can use the LLM's pre-training to your advantage. So we're combining the simplicity of traditional approaches with the power of contextual reasoning that the LLM gives us, which is both scalable and easy to apply. Of course, this is still an early stage exploration, this potential idea, and there are some important limitations to address in future work. The first big one is generalizability. We only tested one LLM, GPT-4o mini, due to resource constraints. We don't know yet how these changes might be affected with larger or different models, but we assume that with more powerful and more smart, let's say, LLMs, the results can only improve. Our experiments also relied on a limited number of benchmarks, and everything was done with Mechtaev. So the findings may not directly generalize to other frameworks or improvement tools. And we only ran single executions per setup, so results may have been influenced by randomness in the GP process. And the second challenge is LLM non-determinism, of course. As we know, LLMs don't always produce the same output, which raises the question about reproducibility and reliability, especially in a search-based search algorithm context. So how do we plan to tackle this? As you can see in the solutions part of the slide. And on the generalizability side, we'll explore more models, more benchmarks, more tools, and more experimental repetitions to validate consistency. And to address the LLM variability, we're looking at prompt engineering and using techniques like temperature control or confidence thresholds to ensure more stable and robust decisions. This works lays the foundation. There's a lot of exciting potential to push further, but we have to keep in mind this is just an initial explorations to see if this direction is viable. So let's sum things up. This study is an initial exploration into using LLMs to assist the crossover process in genetic improvement software. We integrated an LLM into the Magpie framework and observed consistently strong results. We have 8.5% better runtime on average, 25.6% faster at reaching performance milestones, and around 5% more viable variants compared to traditional crossover methods. What makes this very promising is that it all works without retraining, without extra data, and all out of the box just by using the LLM's understanding of code and context. Of course, there's a lot more to be done, especially validating this across the more models and more benchmarks, but we believe this is a solid first step that is showing the LLM-Assisted crossover is a viable and powerful direction for future work in genetic programming. So you can scan the QR in the screen if you want to take a deeper look, try it yourself, and see our artifacts. And at this point, I'll just would like to end the presentation, and I'll take any questions that you potentially might have.
Thank you so much, Dimitrios. So I'll thank the speaker. Very, very interesting talk. I have a couple questions myself, but maybe we can first take some from the audience in the room. And if you have any questions online, we're also monitoring the chat. Any questions in the room? Yes. Want to come up?
So it's Bill Langdon. One of the things that we often neglect from bioinspiration is there are organisms other than humans that have sex. Particularly, there are a class of organisms called slime molds, which seem to have a vast number of different genders and ways of having sex. Have you considered having more than two parents in your crossover? It seemed to me that with LLMs, there was no real reason for limiting it to just two. So maybe you could look at extending to multi-parent crossover.
Yeah, actually, this was an approach that I wanted to test of combining, let's say, my initial idea was to start combining up to 5 parents, but this is the first exploration, and I wanted to make it directly comparable to the traditional approaches, which usually tend to work with two variants, two parent variants on Magpie. So I thought it would be a bit unfair if the first comparative study we have of the traditional approaches with the LLM-assist crossover gave the LLM the inherent advantage of having more parents and more information. But going on from the results of this study that shows that even with two parents, it can perform better, maybe the next step would be to increase the number of parents up to a threshold limit based on the token window of the LLM, and see if that helps us improve the results. This is still a very early exploration of this topic, so I think there's a lot of meat on the bone still, and a lot of different ideas we can explore with how to use LLMs for crossover. But this is an interesting idea, Bill, and I've actually wanted to explore it myself.
Thank you. We have another questions from Epic.
Hi, thank you for your presentation. So you explain how you compound using LLM for crossovers to more traditional crossovers for GI, and you compare the two of them. Did you compare your approach, so crossover with LLM, with simple local search? Because in previous work we compared genetic programming and local search, And we showed that local search was probably better to use. And one of the possible explanation was it may not really work to find new edits independently and then try to recombine them later. And maybe just better to just have one solution and try every new edit on the current one. So yeah, you find that LLM for crossover is better than the traditional one, but did you compare it with just local search?
We didn't compare it with any. The only method used is genetic programming in this study. But I have no reason to believe that if our LLM crossover can improve the results over the traditional methods for genetic programming, why it cannot work for local search as well, considering that there are certain scenarios where using genetic programming is beneficial for the final results. We have seen that in the past. So in those scenarios where genetic programming is beneficial, instead of using the traditional crossover operators, we just switch them with the new LLM-assist crossover operator. So I think this shows that there's a lot of added value just by that. So now your question is if there's specific cases where local search would work better overall. I think that's fair to assume, but that doesn't negate from the fact that the LLM-assist crossover can provide more value in the cases where genetic programming was working better than local search in the first place. I don't know if that makes sense.
Yep. Yeah. Thank you very much.
Do we have any more questions in the room? Feel free to put in the chat. Yeah, ask a question. The slide where you describe the prompt, you have the documentation, you also have the two variants, and you had a couple other bubbles going in there. Maybe we can go back to that slide. I was just wondering, it seems like it would create for a very long prompt. The parent, is that the full program?
The parent is the full program, but no, excuse me, the original variant is the full program, but the parents are only represented by the edits made on the original variant. So you can consider the original variant being quite long, but then the parent one might be that you have deleted one line from line 23, for example, and parent number 2 might be that you have added some sort of line at the line 56. So the parents themselves are simply the diffs of over the original variant, so that really makes the overall prompt smaller. Overall, we didn't have any issues with the token windows. The prompts were quite significantly smaller than the available space we have at prompt.
For very large systems, for example, the Apache projects we're talking about that are multi-file and very big, do you think this would work as well if you just give it the context around the edits that you're making, whether that's like...
Yeah. It's fair to assume that there might be some loss in functionality, but in my experiment so far, I think that the LLM can understand what the functionality and what the purpose the code is trying to achieve without needing to provide the full source code. So I imagine providing some sort of window before and after the edits being made would still provide some value.
Thank you. And my last question is something that I missed, but I was wondering if there were repetitions or if you can comment on statistical significance.
I just said that in the end that due to the time constraints, because we finished experiments just before our submission, we haven't really... Variance does play a role, and we want to validate in future works. And actually, I'm aware of one current work being done at UCL that's going to use our approaches. So hopefully, in the next few months, we'll have some more results validating what we have found here.
Amazing. Thank you so much for that, Dimitrios. Let's thank our speaker again.
Thank you. Thanks for having me.